I'm really just going to focus on one fairly narrow aspect of Martian weather that relates to dust storms in the northern hemisphere and eddies, weather systems that initiate those dust storms. And I also have a co-author, Helen Wang, who did all the image processing, which really will, which adds a lot to this talk. So to introduce the subject, I want to show you some measurements by the MGS thermal emission spectrometer. So each of these panels shows the column opacity of dust, which is one of the things this instrument can measure. It's, and I'm showing you results from Mars year 24 and Mars year 26. I'm focusing on years when there was no major global dust storm. And each panel shows column opacity of dust averaged over longitude, plotted versus latitude from South Pole to North Pole, and plotted versus time over a full Martian year beginning at northern summer solstice. So this is L sub S is just a measure of seasons on Mars. It's 0 at the vernal equinox in the northern hemisphere. And you see a similar pattern in both years. The dark blue is very low dust opacity. The atmosphere is clear. The brighter colors correspond to increasing opacity. These measurements are at infrared wavelengths, 9 microns. And in both years, you see 2 peaks in dust opacity, one in autumn season, one in winter season. And certainly the timing varies from year to year, and the intensity of the dust storms that produce this opacity also varies. But this is a pattern that repeats, and you see it in subsequent measurements by the Themis instrument on Odyssey. So I'll be talking about this autumn dust storm using data from Mars year 27, more recent observations. And at that time, the TESS instrument had stopped sounding the atmosphere, so we don't have this kind of measurement to support us. It's been shown in previous work, analysis of this type of data, mainly by Helen Wang, that these dust storms are, at least the northern hemisphere component of these, are initiated by winter weather systems. I'll call them baroclinic eddies at high northern latitudes. And it's clear also from previous work by Helen Wang, a little bit by me, this seasonal pattern of dust opacity is correlated with the intensity of eddy activity at high northern latitudes, that the eddies tend to have peak intensity in mid-autumn and mid-winter and a lull around winter solstice. So previous analysis has focused on the early years of the MGS mission, and I'm going to focus on the following year. So this is the first close look at atmospheric dynamics in northern autumn of Mars year 27, and my objective is to take a closer look, a more detailed look at the relationship between these dust storms and the properties of the winter weather systems. And I'm going to use data obtained by MGS in its last Martian year of operation, data collected by 2 instruments, the Mars orbiter camera, such as the image in the top, which shows a nice Lee wave at about 55 north at Milankovitch crater. And I'll use atmospheric sounding through radio occultations, and there's an example in the bottom panel. And I'll talk more about this type of display later on. But at this time, MGS TESS was not sounding the atmosphere. The MCS infrared limb sounder on MRO was not yet in operation. We have some observations by Themis, but it's not really an atmospheric sounder. So these are the 2 data sets that we can really use to characterize this season. So I'll begin by discussing these mock images. The instrument had a wide-angle field of view, and all the results are the low-resolution mode of the camera, all the results that I'll show you. And it observed the surface and atmosphere pretty much continuously throughout the mission in both red and blue filters. And it collected, the basic observations are swaths of data on the day side from the South Pole to the North Pole, and each swath is about 30 degrees wide in longitude. And Helen Wang has done the enormous work of applying the instrumental calibration, photometric calibration, and then she takes these swaths and meshes them together as gracefully as she can into what are called Mars daily global maps. And I'm showing two examples in this figure, and the view here is just one quadrant of an equatorial map, and it's centered on Acidalia Basin, which is a low elevation basin in the northern hemisphere of Mars. And I'm going to focus on the latitude range from equator to 60 degrees north, and the longitude range from, this is 120 degrees west to 60 degrees east. So this is sort of the 1/4 of the midsection of the planet. And the point of these images is to show you the appearance of Acidalia and Chrysoplanitia when there's no major dust storm going on. And there's a couple features I want to point out. This is, and this will come up later, this is Alba Patera at about 40 degrees north. It's the visible feature of a large shield volcano at this location. And there's also an interesting low albedo region, Kasai Vallis outflow channel that's a good reference point for gauging the intensity of the dust storms. And these plus symbols, of course, are the landing sites of Viking Lander 1 and Pathfinder, which unfortunately are no longer in operation. So moving on to the dust storms, this shows, it's a 2-day sequence, It's a 2-day sequence showing evolution of a dust storm in Acidalia and Chrysoplanitia. I have a sol is a Martian day, and I've assigned arbitrary numbers to these to help you gauge the time sequence. And I also indicate the season on Mars. This is mid-autumn around LS-215. And in the top panel we see there's a curving band of dust. It appears reddish in these images, and some wave-like structure at high latitudes. This is usually called a frontal dust storm. And it's that wave-like structure indicates that it's associated with those weather systems at northern mid to high latitudes. In the lower panel, the observations on the next day, you see this dust storm has moved southward. It's reached the latitude of the two landers. It's more diffuse and covers a larger area than the frontal dust storm, and you'll notice a linear dust feature extending to the northeast. This is typical structure of this type of storm, which is often called a flushing dust storm. And you can see the bright blue colors are water ice clouds. The dust appears more reddish in these frames. And if you toggle back and forth, you look at the top frame, you can see this dust storm. And in the bottom frame, it helps you identify where it is. It takes a little bit of training to recognize sometimes where these dust storms occur, and that's especially true later in the season when the whole atmosphere becomes more opaque due to dust, and the surface has a hazier appearance. But in a previous talk, I got tired of toggling back and forth like this to show people where the storms were, so I just went ahead and took the difference between the pairs of images to see what would happen. And it actually works pretty well. I've taken the difference, I've clipped it and stretched it a little to try and bring out the dust features. And you can see that in the lower panel, this has worked quite well, and I've pretty much rubbed out the entire surface of Mars. All you see is the bright region corresponding to this dust storm. So you can see in that frame it works pretty well. And if you have the opportunity to scan through these images and jump back and forth, you can train your eye to recognize these storms. In the top panel, certainly this band of dust, the frontal storm shows up very clearly, but you also see some artifacts from the surface, and that's the problem with this approach. You'll see these artifacts. Here's this Graeus Mons. You see these artifacts when the viewing geometry and solar illumination have changed a little bit between the reference frames. But I think it's a useful tool for helping to locate these dust storms. Now, this type of dust storm, characterized by this 2-day sequence, occurred repeatedly in autumn of Mars year 27, and it's similar in some respects to dust storms observed in previous years in connection with this mid-autumn dust storm. But it's also, the behavior this year, I think, was unique in some ways, in that somewhat later in autumn, these dust storms became intense and very regular. So I want to show you some examples of that structure. So this is I'm going to show you a 4-day sequence of dust storm activity beginning, this is about 2 weeks after the previous slide. This is Sol number 35. It's about LS 224. And the top panel is the MDGM produced by Helen Wang. In the bottom panel, I've differenced that frame with a subsequent reference image to try and enhance the dust storm. But you see there's a sort of lobe of dust in Acidalia, some wave-like structure at high latitudes. This has the appearance of a frontal storm, although it's not as tightly organized as the example I showed you previously. And you see the outflow channel of Kasai Vallis, easy to identify in this frame. And in the bottom frame, this helps you see where the structure of the dust. And there's a suggestion of sort of diffuse dust in Chrysoplanitia from previous dust storm events. Okay, the following day, this is Sol 36, you see the dust storm has moved southward. It extends almost to the equator. And it's similar to the Flushing storm that I showed you previously, although it covers a larger area and it seems more intense. You can see it's pretty much obscured this excuse me, the outflow channel of Kasai Vallis. And it extends well past the landers, almost to the equator. You see a sort of linear band of dust to the northeast as before. And the bottom panel helps bring out some of the fine structure in this dust storm. I think there's evidence for convective activity, and I'm not sure this image is trying to tell me something, but I can't explain, what this structure in the storm means. So this is the second day of the sequence. The third day of the sequence looks very much like the first day, where you're back to seeing this frontal type structure, wave-like structure in the north with a concentration of dust in Acidalia. You can see it here. And the fourth day of the sequence looks like the second day, where you have this an even more energetic dust storm now extending beyond the equator with lots of interesting structure in it, this band to the northeast. And so if I toggle through these, I think you'll get a sense of a 2-day periodicity in the structure of these dust storms. So I hope you can see that clearly. And I think these difference frames do help. So I think I'm in the process of looking through, it's something like 150 days of these kind of images to try and train my eye to identify storms and put them in categories, and I'm getting help from Helen Wang on doing this. So we're putting together a catalog of these dust storms, their sequence of occurrence, and putting them into categories by their structure to correlate with other observations. And a couple of key findings from this period: these regional dust storms like the ones I showed you occurred in all 3 major topographic basins of the northern hemisphere, Acidalia, Arcadia, and Utopia, in these data from Mars year 27. But their distribution is not uniform. Most of them occurred in Acidalia 7, with 2 in Arcadia and 1 in Utopia. And as I showed you in that last 4-day sequence during LS 221 to 226, this is, by my counting scheme, sols 31 to 38. These dynamic regional dust storms occur repeatedly in acidalia, and they consist of this frontal flushing sequence with a 2-day periodicity. So these are features that I'll try and explain in the rest of the talk in terms of the behavior of the weather systems. And so in the remainder of the talk, I will be using radio occultation data to characterize the dynamics of the atmosphere. But first, I want to introduce a couple concepts about the atmospheric circulation. And to do that, I'm going to refer again to measurements by the MGS thermal emission spectrometer. This is temperature cross-section from LS-270, that's northern winter solstice, in the first year of MGS operations. So that's Mars year 24. And what I'm showing here is temperatures that are averaged over longitude. They're plotted versus latitude from South Pole to North Pole, plotted vertically using log pressure from, this is the surface, to an altitude of roughly 60 kilometers. And you see these are temperature contours in Kelvin, 10 Kelvin per contour, and they're clearly labeled. And of course, at northern winter, the temperatures are warmest in the south and quite cold in the north, down to CO2 saturation. And this, the thermal structure is a response of the atmosphere to direct solar heating, which is of course concentrated in the southern hemisphere. And this temperature field also is modified by the attempt of the atmosphere to redistribute that heat. And there are two aspects of the dynamics that I want to point out here. One occurs at high northern latitudes. You'll notice temperatures decrease from south to north, but the temperature gradient is strongest at northern mid-latitudes. And this configuration can become unstable, and that produces weather systems, frontal structures, the kind of weather systems that we're familiar with here, or if we were having any rain. And this sort of instability on Mars will produce eastward-traveling wave-like structures, and I'll say a lot more about that in this talk. But the winds associated with these weather systems initiate the dust storms that I was just showing you. The second component of this circulation that's also important for the behavior of these dust storms is what's called the Hadley Circulation, and it's intuitively more obvious. This sunlight heats the atmosphere south of the equator. The warm air rises, travels northward across the equator at high altitude, descends in the north, and then there's a return flow concentrated close to the surface that completes this cycle. And this is the attempt of the atmosphere just to redistribute the heat more uniformly. But that southward return flow of the Hadley circulation also has a strong influence on these dust storms. And here's a cartoon schematic I found of the Hadley circulation, and unfortunately it happens to be southern summer, which shows this return flow near the surface. Okay. Now, these figures show measurements from previous years concerning the spatial structure of these weather systems in the northern hemisphere. And these were constructed from radio occultation measurements. And I'm showing you these rather than Mars year 27 because these were already done when I pulled together the talk. And so each panel shows a temperature field versus longitude and log pressure. This is altitude. It corresponds roughly to altitude from the surface to 25 or 30 kilometers. And I've subtracted basically the zonal mean temperature, and I'm in a reference frame. This isn't longitude attached to Mars. It's a frame that's rotating relative to Mars, traveling eastward at the phase speed of these disturbances to give you a sense of what their structure looks like. So I've averaged some data over 10 or 15 days to derive this sort of structure. And the top panel is this is early autumn of Mars year 26. It's at constant latitude, 69 degrees north. And the structure in this case is it's zonal wave number 2. There are 2 cycles of oscillation per 360 degrees of equivalent longitude. The amplitude is quite large. This is temperature in Kelvin. The shading is for positive, and the white is for negative temperatures. The amplitude here is 10 Kelvin. The bottom panel shows analogous measurements from midwinter of Mars year 25, 63 degrees north. In this case, we see 3 cycles of oscillation around a latitude circle. It's a wave 3 disturbance. The amplitude's 5 or 6 Kelvin. In both cases, you see the temperature field is concentrated near the surface, the lowest 5 or 10 kilometers of the atmosphere. And this type of structure is, I think, is characteristic of a wave-like disturbance that arises from what's called baroclinic instability. Its appearance is similar to simple models such as Charney waves. So I tend to call these baroclinic eddies, and the terminology is a little obscure, but that's a convenient way to refer to them. Now, the measurements I'm going to show you in the rest of the talk are at a pressure level of 610 pascals, constant pressure. That's the red dashed line. It's close to the surface, so it's relevant to processes that lift dust. And it's also, you can see it's near the peak amplitude of the temperature field. So it's a level where these eddies are intense, and they're close enough to the ground to influence dust storms. So I'm not going to talk about temperature anymore. I'm going to show you a different type of measurement that I think is more informative for understanding these baroclinic eddies. And it's something called geopotential height, measured in meters. This shows measurements of this quantity as a function of time in sols using the same references in the previous figures. So this sequence is subsequent to those dust storms that I showed you previously. Geopotential height just is a measure of the elevation of this surface of constant pressure. And you can see it varies quite a bit, plus minus 300 to 600 meters. And this is how the atmospheric dynamics perturb this surface of constant pressure. So we're really just measuring its elevation. And I've removed a trend from these data to show the variations caused by baroclinic eddies, and it turns out stationary waves as well. And these data, the way they're collected, it's a little bit peculiar, but you can imagine as time goes by, we make measurements, and at the same time, our longitude of the measurement is drifting steadily westward as the planet rotates. So we have this correlation between time of observation and longitude of measurement that causes some problems, but it's at least a problem that's been studied before in terrestrial observations in papers such as these by Chapman, Salby, Leighton Stanford. And the method I used to analyze these data is described in a paper from a few years ago. I've really just taken there's nothing new there. I've really just taken these earlier techniques, applied them to this type of measurement. And the results are most easy to understand when you look at the spectrum of these variations in geopotential height. And I use a method of least square spectral analysis that's based on these previous techniques. So when you apply that technique to this segment of data, you can calculate a spectrum. This is, I've turned it on its side for reasons that'll be clear in a moment, but what I'm plotting in here is the spectral power versus the frequency. And again, this is geopotential height at 610 pascals, a few kilometers above the surface, and I've expressed it in terms of a frequency cycles per sol observed from a polar orbit at fixed local time. And as I mentioned before, the measurement longitude varies systematically with the time of observation. This is what polar orbiters do. And The difficulty we have is that we can measure this frequency directly, but it doesn't give us a unique solution for the zonal wave number S of these baroclinic eddies, or the frequency sigma that would be observed from a fixed location on the surface. It gives us a constraint, that the frequency we observe is a combination of time variations and spatial variations, which produce time variations because of rotation of the planet. So we can resolve this ambiguity, fortunately, because we have previous measurements, such as by Viking landers, by the MGS thermal emission spectrometer. So we know that these baroclinic eddies travel eastward. We know that they have periods observed from the surface of typically 2 to 10 Martian days. So using that information, I can identify for the main spectral peaks the most likely values of zonal wave number and frequency sigma observed from the surface. And as an example, this peak at 2.0 cycles per sol in frequency F is a stationary wave. It's zonal wave number 2. Its frequency sigma is 0. And as the planet rotates, you just see the pressure ridges come by twice per Martian day. The other peaks correspond to baroclinic eddies. And I've picked this example because it's a little bit peculiar. You see 3 peaks, one at zonal wave number 3, one at zonal wave number 2, another at zonal wave number 1. They all have the same period. And this is just the mathematical signature of a wave 3 eddy whose amplitude varies with longitude. So there aren't really, I wouldn't consider these to be 3 distinct eddy modes. It's just a mathematical representation of a mode that has more complicated structure. So this shows results from an 8-degree window in L sub S. I applied this to the whole season of data, and we get the results in the next slide, where again this is the same frequency scale as the previous slide, the frequency observed from orbit in cycles per sol, and then I've annotated it to show values of zonal wave number and the frequency sigma observed from the surface that are deduced from other information, the Viking landers especially. And this shows results from LS, this is a time axis, so we're going from LS 150 in late northern summer through LS 270 winter solstice. The latitude of the measurements wandered around a little, but it stayed within this band of 65 to 75 degrees north. And so these bland regions are where there's not much going on, and the brighter regions where I've added contours show the main spectral peaks. And the interval that I just talked about was in this sort of roughly 230 to 240 range, and you see the same peaks in there. So there are basically two types of dynamics that appear in here. One is stationary waves. You see them at zonal wave number 1, frequency 0, so the stationary waves are right along this dashed line. And you see the first disturbance of the season is this very strong zonal wave 1 stationary wave. That's something that repeats every year. And there's also stationary waves at zonal wave number 2, which strengthen later on. And you can see there's some interesting time variation in the behavior of the stationary waves near the surface. The rest of the spectral peaks in this figure are due to eastward-traveling baroclinic eddies. And I think what's most interesting about this feature, or this figure, is the way it shows that these the weather is characterized by transitions among these eddy modes with different values of zonal wave number and frequency. And it progresses through these modes as the season goes by. For instance, around LS 185, the dominant baroclinic eddy has zonal wave number 2, and this is a period of about 2.5 Martian days. As that fades, it's replaced by a very strong zonal wave 1 eddy with a period of about 7 or 8 Martian days. And then there's a subsequent transition at LS 215 or 220 where the wave 3 mode becomes dominant. And this has a period very close to 2 days. After that, there's a shift in frequency, but still a wave 3 mode, and then that fades and you're back to a wave 1 mode. So there's this interesting progression among modes with different zonal wave numbers and periods. And the second interesting feature is that I can annotate this figure to show when those dust storms occurred, the strong flushing dust storms that I described previously. And there were a number of these. I think there's, 9 lines in here. You can see most of these occur in connection with this strong wave 3 mode that has a period of very close to 2 Martian days. And that accounts for the periodicity of those dust storms. As to why the storms stop so abruptly, I don't have an answer for that, but that's a very interesting question for future work. So a few conclusions from these last few slides. I think I've already made the first point. There's this interesting sequence of transitions among eddy modes. It's an important basic property of Martian weather. It hasn't received that much attention. It was first pointed out in a paper by Collins et al. In 1996, who looked at and attempted to simulate the Viking lander measurements. And I've raised this issue previously, and I think this is an important property in part because these mode transitions have a strong influence on the timing of those regional dust storms. And in particular, this large amplitude wave 3 mode results in very strong meridional winds and favorable conditions for dust storms. And I'll explain that point or justify that claim in the following slides. But what I want to do in the next few slides is really focus on this particular eddy mode and show you in more detail what its behavior is like, some of its key properties. And I'll do this again using measurements of geopotential height at the 610 Pascal pressure level. This is similar to a figure I showed you earlier, but now I'm looking at that interval LS 220 to 228 when that wave 3 mode and the dust storms are strongest. This is at 65 degrees north, fixed local time, geopotential height in meters, and time span covering 12 Martian days. The dots are actual measurements. I connect them by lines when we have measurements on consecutive orbits, and you can see there were very few gaps in this sequence of data. The thing that stands out when you first look at this is the strong peaks in geopotential height that occur every 2 days. Of course, that's the period of the eddy mode, but these peaks reach about 900 meters, which is quite substantial. So one way to characterize these waves is to reconstruct the waveform, which I've done in the lower panel. And I do that by looking at the spectrum of these data, identifying the main peaks in the spectrum, and for each peak, estimate the amplitude, the phase, the zonal wave number, the period of that component of the spectrum, and then simply add them back together in the time domain. And this is the reconstructed waveform that I'm showing in the lower panel. It's the same display. You can see it does a reasonably good job of matching the measurements. You don't have to look too closely to recognize there are some differences, but we certainly pick up these strong peaks that occur every 2 days. And I think it's a reasonable representation, and it's very convenient, as I'll show you, as a way of illustrating the behavior of this eddy mode. So the first thing we can do is look at the time evolution of this eastward traveling wave 3 baroclinic eddy. And I do that by plotting, for the reconstructed waveform, plotting geopotential height versus east longitude on Mars. This is at constant latitude again. And I'm showing the snapshots of the waveform at 8 time steps over the 2-sol period of the disturbance. So that's what this family of curves is. I've color-coded a couple of those to help you pick them out. And there's 2 important points here. One is As you can see, the amplitude varies significantly with longitude, and this is presumably due to interaction of the eddy modes with topography, such as Alba Mons volcano. And this is a subject that's been discussed through numerical simulations by Jeff Hollingsworth, and I think now that we have measurements of this sort, I think it would be worthwhile to take another look at that kind of behavior. And for example, if you look at the red curve, this strong peak of geopotential height occurs when you have a ridge aligned with the longitude of Alba Mons. And so that explains those peculiar peaks in the geopotential field. The second point to note is that this waveform is not symmetric about zero, and that's due to the effect of the stationary waves, especially the wave 2 structure, which gives it this sort of wave 2 bias in this type of display. So one of the reasons this type of measurement is convenient is that a measurement of geopotential height versus longitude allows you to estimate the north-south component of the wind field, and it's proportional to the slope of the curve at any particular longitude. So it's pretty straightforward to estimate the wind field from these type of measurements. And I think in this case, it's a reasonably good approximation. So on the next slide, I've done that. This shows meridional wind speed from minus 30 to plus 30 meters per second. This is positive northward. And this is meridional winds implied by geostrophic balance. That's an approximation that I think works pretty well near the surface of Mars at least. So the meridional wind speed V just depends. This is the derivative of geopotential height with respect to longitude. And then there are some constants like the latitude of the measurement, the rotation period of Mars that we know very well. So this is a simple calculation. But in this figure, I'm showing only the traveling wave. And you can see its amplitude varies with longitude as you would expect. The winds are strongest at the longitude of Alba Mons, where they're plus minus 25 meters per second. This is roughly the threshold that people think is required to raise dust from the surface. The winds are much weaker near Utopia Planitia, only plus minus 15 meters per second. It becomes more interesting when you include the stationary wave, and that's what's shown here, the same meridional wind speed versus longitude, 8 time steps. And the effect of the wave 2 stationary wave is to make the circulation around Alba Mons asymmetric. In Arcadia, there's now a northward bias to the winds. Peak northward winds are about 30 meters per second. The southward winds in the Arcadia Basin are only about half as large. In Acidalia, the reverse is true. Now there's a southward bias to the wind field, peak winds at 25 or 30 meters per second, but the northward winds are only 10 or 15 meters per second. And this will, it seems to me, will influence the location of those dust storms. It puts a strong bias in favor of dust storms in Acidalia, where these southward winds are strongest. So this red curve corresponds to the situation when there's a geopotential ridge at Alba Mons, and then you get a very strong clockwise circulation northward through Arcadia, turning eastward north of Alba Mons, and then southward toward Acidalia. And when the winds are in that configuration, that corresponds to the days when we see those strong flushing dust storms. So another set of conclusions here. This asymmetry of the wind field around Alba Mons, it seems to me, will favor regional dust storms in Acidalia, at least in this set of observations, and it will tend to inhibit them in Arcadia and Utopia. And that's consistent with the observations. The stationary zonal wave number 2, stationary waves play an important role in this behavior. And maybe I could jump back and show. So here's the strong wave 3 eddies I've been describing. here's the wave 2 stationary wave. It's interesting to me the way these tend to peak simultaneously, and I wonder if there's some sort of interaction or reinforcement going on there, but that's speculation at the moment. And here we are. So maybe the main conclusion of the talk is the strong asymmetric winds associated with the wave 3 baroclinic eddies influence both the timing and the location of these regional dust storms in the large topographic basins of the northern hemisphere. And it's certainly consistent with the previous work by Helen Wang, but it has established a much more detailed connection between the baroclinic eddies and the dust storms. There's one other topic I wanted to forge through, but I think maybe I'll close with one view graph that shows some future directions. And if you want to know, I had some speculation in the previous slides about why the dust storms stop, but you can come ask me later if you want to know more about that. But I've thought about where to go from here with these observations. One thing to do is to look at measurements from previous years in light of these results, especially to try and understand why the timing and intensity of those dust storms varies from year to year. And there are a few key questions here. What mechanism causes these baroclinic mode transitions? It has a strong effect on the dust storms and the climate of Mars. I don't understand in detail how the topography produces this particular modulation of the wave 3 eddy modes, but again, that has an influence on the location and timing of the dust storms. And another question is, why do these dust storms stop when they do? I think numerical simulations that I've looked at so far sometimes do a good job of starting dust storms at the right time in the right location, but once they get going, they never stop. And so this is an important question to answer. And I'd like to, having gone through these steps of data analysis, like to begin to compare the results with simulations by general circulation models. And if we're able to validate the models, that would be a good approach to answering some of these questions. And so the major goal here is to improve our understanding of regional dust storms and our ability to simulate those. And maybe this is a step toward understanding the really large dust storms that occur in some Martian years, but not others. So I think that's a good place to stop for questions.
Do your studies suggest that there are some areas of Mars that we shouldn't be sending spacecraft to versus places where we could, and would that potentially pose an possibly insurmountable bias in the way particularly surface missions are assigned?
That's a good question. I think for someone like me who's interested in the atmosphere, I may want to go to some of these places and find out more and just make sure the spacecraft is designed to survive this kind of dust storm. I think there are two issues for the broader objectives, which looking for life on Mars, or one has to do with when and where you land, and these kind of dust storms would be a big issue that would limit your ability to land in certain locations at certain times. So that's one problem. And then, of course, as I referred to before, just making sure that you know the range of conditions you might experience once you're on the ground so that you can make it through that dust storm without running out of power or whatever. But certainly this kind of modeling is being used to guide selection of landing sites for MSL. Fortunately, it's at a season where not much is going on in the way of dust storms, so it's not as much of a problem.
Do we have other questions? With Spirit and Opportunity, we heard a lot about dust devils clearing off the solar panels. Are dust devils associated with these kinds of storms, or are we looking at something completely, or much smaller intensity?
I think it's a completely different phenomenon, and they tend to occur rather than autumn and winter, they tend to occur in summer, where the sunlight intensely heats the surface, and the atmosphere is trying to carry that heat away, and those vortices form. That's just the response of the atmosphere to transport heat vertically. And when they lift dust, you can see them, and they're quite widespread. There was a question here in the...
What is the reduction in sunlight intensity during one of these storms? Would that affect solar electric production?
Yeah, it certainly would affect it. I think of visible opacity at the... This would be a good point to step back and say, I'm showing you this a narrow picture of what's going on. There are other things interesting going on at the same time. So in addition to these regional dust storms in the northern hemisphere, toward the end of that episode of dust storms, additional dust storms began to occur in the south, in the usual places around the Hellas Basin, around the edge of the south seasonal polar cap, which is receding. And the net effect of these storms was to produce a haze that pretty much covered the planet. And I would say the optical depth might have been sort of 1/2 to 1, something like that. Although I don't know how to get an opacity out of these images. It's not an easy thing to do. But certainly if you look through, as you scan through the sequence, you notice that the surface is becoming obscured by dust. You can still see the features, but they're pretty hazy.
What are the wind speeds associated with these dust storms? Do we have any information on that?
Well, you can estimate winds from geostrophic balance like I did, but that's just the north-south component, and that can reach, for some of these, the most intense cases, it can reach about 30 meters per second. Those happen occasionally. I mean, those wind gusts happen occasionally, not that often. I think you really need to look at a numerical model to help you fill in what the other wind speeds are like. I think the Hadley Circulation return flow can be of order 10 meters per second near the surface at lower latitudes. There's a strong zonal wind jet at high northern latitudes that near the surface is also perhaps 10 meters per second. So when you add these together, I think you could get wind gusts of 40 meters a second, just not very often. The density is pretty low, so if you were standing there, you'd hardly notice, but maybe. You'd notice the dust less than the wind, I think, or dust more than the wind.
Thanks, Dave, for a very motivating talk on Martian weather. One thing I just wanted to bring out is you talked about the fronts and low pressure systems. For what we know about the Earth's meteorology, they come in pairs. You don't have a front or a low pressure system without the high pressure system or the anticyclone, which we're currently enjoying right now outside.
Mm-hmm. Yeah.
And it's interesting the correlation of those flushing events where the winds appear to be predominantly from the north towards the south might be representative of the anticyclone becoming in that position in its favor to bring that material down towards the low latitudes. So you often have to think of these baroclinic waves as pairs of highs and lows don't do everything, highs do things as well.
Right.
So, the other thing I just want to mention real quick is this modulation with the topography. It's interesting that there's a wave 2 strong signature. The low-lying basins sort of have a wave 3 structure to them, and the deformation scale of these waves is about that in terms of a zonal wave number. So it's maybe like a chicken and the egg question, what came first? Are those eroded preferential regions? That's up for debate, because the scale of the storms just kind of fit right in those low-lying basins. But
Yeah, I think that's an interesting point that hadn't occurred to me, but I think I pointed out how the wave 3 modes have this strong modulation of amplitude with longitude, which is presumably due to some coupling with the surface. And I don't tend to see that behavior in the wave 1 or the wave 2 modes. They're much more zonally uniform. But the first point you made, actually on Mars, I'm not sure they come in pairs. They tend to set up a continuous chain that once one of these modes is locked in, you just have, for an observer on the surface, you'd see a high, a low, a high, a low. And for a period of 15 or 20 sols, when one mode dominates, those variations are very regular. So if you're a weather forecaster, once one of those systems set up, you could just say, tomorrow we're going to get a high, and the next day we'll get a low. And certainly, I agree with your point about the effect of the highs and the lows together, that it seems to be when the stationary wave tends to want to, wave 2 tends to want to put a pressure ridge on Alba Mons and just stay there. And so when the eddies come by and their ridge aligns with Alba Mons, you get that strong clockwise flow around that shield volcano, or north of it. So.
Would you expect the same kind of results to be mirrored in the southern hemisphere?
What I expect, I'll leave that part out. I'd say what we observe is something completely different. So I've left that out. There's this real interesting asymmetry between the winter weather in the north and the south. And maybe that's a subject for a future talk by somebody else, I don't know. But it is quite different, and maybe it's partly the influence of, say, enormous basins like Hellas that the topography will affect the behavior of the waves, but it's not, I don't understand why the difference is there. I just know that they're quite different. I know Jeff Hollingsworth has studied that question more closely than me, so maybe you could ask him after the talk.